actually gives me great pleasure to talk about Hema, especially on this day at RRI. Many of us know her and knew her personally as well. So I don't think she needs an introduction to the wider audience here. So I'll just directly go to the talk. So Professor Hema Ramachandran, Hema to all who knew her, left us on November 24th, 2020, after a long battle with cancer. The Light and Matter Physics group was started by her. Of course, it was called Optics Group then. And so she was one of the founding members of the Light and Matter Physics group, and she's a fine scientist as well. So just thinking about her life, I realized that she was a feminist not only through her scientific work, but also through her everyday life. And she walked a path which was rarely taken by women of her times. Looking back, it has become very, very obvious to me that very few people would have done what she managed to do. So I will mostly spend time on the kind of science she did at RFI with some brief snippets of what I know about her life. Right. So this Hema had an MSc degree from IIT Bombay, and thereafter she joined BRC training school as part of getting her PhD and being at BRC as well. And she initially worked in the area of experimental high pressure physics. Yeah, there she through the paper I understand that she uncovered a novel phenomena where when a material is subjected to high pressure, it actually becomes amorphous. It usually can turn crystalline, but it turned amorphous. And this particular work seems to have gathered wider recognition, and she was awarded an Young Scientist Award for this work. And during that time, she got married as well. So she moved to Bangalore, where her husband worked, and BRC stationed her at the Seismological Center at Gauribidnur. And during that time, the scientists at Gauribidnur had an office at RRI. So that's how Hema's connection at RRI began. And in 1995, she was offered a faculty position at RRI by the then director to actually start an optics group, which was not there till then. So I was just doing my PhD when Hema joined, final year of my PhD when Hema joined RRI, and I submitted a year after that. And when I was applying for postdoc, Professor Kumar came and asked me, there is this upcoming optics lab. Would you like to come and help Hema start an experiment? Because Professor Kumar strongly believed that there should be an ongoing experiment. The science should be there all the time while you're doing other stuff as well, which I think something which we all inculcated in the course of our overlap with him. So this is one of the first experiment myself and Hema did at RRI. When I met her first, as I was recalling yesterday, when I met her first, I realized that this was a driven, ambitious person with a rare dose of personal warmth as well. There's always this, she always cared about you beyond, the actual thing which she is engaging you with, which actually is very endearing. So, so this was one of the first experiments we did, and coming from theory PhD, I got the maximum fun out of doing this experiment, I can say now. So the goal of the experiment was to image an opaque object inside a turbid medium. So when you try to, typically a turbid medium by definition has many scatterers in it for the light to scatter. And so the light typically takes a diffusive path inside the medium. So in a diffusive scattering regime, what happens is very soon after the first few scattering, the photon loses its memory of the incident polarization and its direction of propagation. It just gets randomized. And so it won't carry the shadow of the opaque object which was kept inside the medium. And people already were trying to do this imaging of diffuse objects kept inside a turbid medium. And one of the things which they did was to catch these so-called ballistic and snake photons. So what are they? So in the presence of many scatterings and many scatterers, there exists non-vanishing number of paths, which are the so-called ballistic and snake paths. The ballistic paths are those paths which those very few paths, exponentially small number of paths, wherein an incident photon doesn't get scattered at all, despite the existence of many scatterers. Uh, the take-home message is that such scattering paths do exist, yeah. And more numerous than the ballistic path is the so-called snake paths, wherein the photon does scatter, but it suffers fewer scattering. So what people did prior to Hema doing this experiment is that people time gated to get this opaque image of the object. By time gating, they synchronized the source and the detector in such a manner with a suitable delay depending on the length of the object. Which you're trying to image, which is inside this turbid media, so such that your shutter will be open to the detector only for a very short time. The shorter the time is, the greater the probability it will catch this ballistic and snake photons, because those would be arrive first, because they are not getting scattered. They are not suffering many scatterings. So time gating was the preferred method, and thereafter people already had done, apart from us trying to do this experiment, people had already done also what is spatial filtering. So the original direction of photons are those which preserve the direction, which would be the ballistic and snake photons, and those can be filtered out by having a spatial aperture at the appropriate distance from an imaging optics. So this was also something which already existed. So what Hema's original idea was, she said, let's do the time gating, and the time gating was complicated to deploy, in the field, so to say, because you need to carry the electronics for the shutters, for the fast shutters, and the faster the shutter is, the costlier the equipment was, and so on and so forth. So she said, let's do the time gating, but not in the temporal domain, but not in the time domain, but in the frequency domain. Yeah. So this was her idea. So we did manage to put a timestamp on the incident photon, and the timestamp was putting rotating, changing the one of the variables of the light, in this case the polarization variable, in time by having a rotating polarizer, and looking in the image plane, in the CCD plane, at each pixel at the appropriate Fourier component. So you collect large number of data, come home and load it on the computer and do the Fourier transform and look at the pixel image or value at that appropriate Fourier transform frequency. Of course, there is a suitable analyzer on the other end which discriminated the polarized light from the unpolarized background, which the scattered photon which give. So after many trials, we managed to find the appropriate time about which we have to take the data, and the intensity and the aperture size and so on and so forth. And we're very happy to see, for example, here A, B, and C and D are. This A shows the image, bare image, without anything on the CCD camera, without doing anything. Just put a CCD, look at it. How does it look? It looks nothing. Nothing, no image comes. And then in image B is the DC image, that is the zeroth order Fourier component. So it'll give the light which just managed to either specular reflection or stuff which are coming from other things other than the turbid media. And image C is the one which actually is at the right Fourier component, and image D is the one without the turbid media. So this was an IC leg. If you have seen an IC, this was just an IC which was put inside, and this was an IC leg. So we were very happy doing this experiment, and it got published as well. And so that started Hema's association with light scattering in random media. I would say this was something which she always wanted to do and did in some form or the other till very late in her life. So one of the other things which Hema's group did, which I was not involved in, but which attracted wider national and international attention, is this finding out what kind of intensity statistics does a light which travels through something called a random amplifying medium exhibit. Yeah, a random amplifying medium is not an amplifying medium where the amplification scatterers are situated randomly, positionally, and but each of the scatterers not only scatters light, it also amplifies the light. Yeah. So along with every amplification, the fluctuations associated also amplifies more typically, because these are random amplifying medium. And so the question that was asked in this publication, which I think Hema did with her student along with Professor N. Kumar, is the fact that what kind of the intensity fluctuations do these statistics of light coming out of such random amplifying medium show. And they found that contrary to usual expectation, which should be Gaussian statistics, uh, due to the underlying nature of a large number of scattering events present in such dense media, um, it was for appropriate, concentration of the scatterers and appropriate gain parameters. It was showing a Levy statistic. Levy statistic, you can imagine as a Gaussian with a fat tail on one end. Yeah. So all of us who were intensely, talking about this experiment at that time in RRI, things where people talked about their experiments animatedly, and so a lot of discussion happened even with people who are not, directly involved in the experiments. So we and Professor Kumar used to call it as larger than rare paths. So again, this, one of the rare paths is what contributes, but the rare path is exponentially rare, but then it has a exponentially larger gain. It also, so the rarity of the path and the largeness of the gain is what gave rise to the Levy statistics. And I think the larger community, as well as Hema students themselves, along with Hema and Professor Kumar, benefited immensely from this experiment. And we all learned, for the first time, we learned statistical optics in an experimental setting, I must say that. So thereafter, I went for a postdoc and then came back. And then Hema by then was well into procuring experimental apparatus for starting laser cooling of atoms at RRI, which Professor Kumar wanted to do. And so prior to actually doing the experiment, we also got into reading material about Bose-Einstein condensation, and it actually resulted in a paper where me and Hema jointly published this paper, which I won't go into details, but just to say that we were also side by side trying to understand as much theory about this as possible, and trying to start the experiment as well. I joined the faculty at RRI in 2001, and just to tell you how naive we were when we started the experiment. We were building external cavity diode lasers, and the laser which was deployed to get our first magneto-optically trapped cold atoms was home built. So the previous day when we saw before we saw the mod, our so-called repumper home built laser broke down, and Hema actually stayed back and put the laser diode back and got the fluorescence and so on. So I would say that it was a period of high enthusiasm and blind optimism, which I think as years goes by, we also grow jaded, but this is a very important ingredient for doing good science, is what retrospectively I would imagine that it's true. So a lot of enthusiasm, and we can do anything optimism, and of course driven by such stalwarts like Professor Kumar and Professor R. Srinivas. So this is a team which managed to get the first MOT at RRI way back in October 2001. And all of you will recognize all the figures present, just for completeness. This is Meena, who was our technical support at that time. I think any number of vacuum experiments, vacuum setups or arrangements were broken and remade with the help of Meena. And this is me, and this is Professor Kumar. This is Professor R. Srinivasan, and this is Chandrasekhar, who is now a faculty at IMC Chennai, and he was a project student before he got his Rhodes Scholarship. And this is Professor Hema herself. So, and after getting the MOT, it was boost in the arm, so to say. So we went on to do spectroscopic measurements with cold atoms, and I think it was a high period of doing cold atom experiments for me, at least at RRI. So Hema then thereafter dwelled into what kind of experiments one should do if at all we manage to achieve Bose-Einstein condensation. And one of the things she came up with, again, it was her original idea. So to find out, I mean, when let's say you have you shine laser, and in some with some manipulation of laser parameters interacting with the atom, it's possible to make laser induced collisions of the atom. So when two atoms come very close to each other, the individual energy levels will also change. And then imagine that let's say you have a laser light which is not resonant with let's say two kind of atoms which are present, let's say one rubidium and one cesium atom. But then when these atoms come together, for appropriate frequencies of the laser, which is not resonant with either of the atoms when they are far away, now they can absorb two of these photons and go to their respective resonant energy levels. Yeah, resonance as described when they are far away. Yeah? So this was before boring you. I mean, I don't want to bore you with details. This is what is called non-resonant absorption of photon pairs. Just on one line, this is collective absorption of more than one atom of a non-resonant light, a pair of photons in this case, and so that each of the atoms can go to their individual excited states. Yeah. So this idea already existed, and Hema made use of this idea to come up with the quantum logical gate operation, which is a universal gate as well, which is a CNOT gate, and it was published. And in this paper, apart from me, Hema, and Professor Srinivasan, Anders Kasberg, whom many of us know here, who was a visiting professor at RRI some years back, he was also involved in this work. So just to tell you that our interests were not only in getting the MOT experiment and all. It was also into proposing ideas for in the cold atom setup. And then, of course, it was natural to talk about quantum walks with cold atoms, and this particular paper, which she did with her student, came out with a proposal wherein you can find out quantum walks in, again, cold atoms in optical lattice by not looking at positional displacements of positional displacement, but looking at internal energy states. Yeah. So this was also, again, one thing which started Hema's foray into quantum walks, and she also did another experiment just with light and with no atoms. This is, establishing quantum walks in frequency domain using what are called acoustoptic modulators and Michelson interferometers. Yeah. So using these two arrangements, she managed to reproduce a quantum walk in frequency domain, even though with a classical light, and then went on to show that even if you deploy a single photon source, the results would be exactly the same. Yeah. So this was done again with one of our later graduate students, Deepak. Right. So Hema, as we all know, did a lot of other things other than these particular experiments, which of course a lot of time goes on in doing an experiment, getting a publishable result out. So she, during her later years, she wanted to do a brain-computer interface research at RRI, and she started this activity. And several of EEG members were involved in it. She was also collaborating with hospitals like Aster Hospital in Bangalore, where she would get data. And I was not involved in this, so I cannot go and tell you what exactly she did here. And she also had active collaboration with scientists at TIFR, Mumbai. And one of the things which they did, which caught all of our attention, was to how, a photothermally created bubble, air bubble, how it cavitates, and what is the kind of light emitted from such bubbles. And so that was also one of the interesting experiments, which I think got published in, I forget now which journal. So as I said before, prior to coming to RRI, she was conducting seismological data. And I distinctly remember there was just one computer center at RRI, and I was just writing my thesis. So all of us would stay back late at night, well beyond we would go at 2 a.m. or something like that. And Hema, during most of these days, would stay till 9 p.m. and would be analyzing reams of seismological data. And amidst our, we'd be shouting, screaming, like all graduate students do of that age, I guess. So, but she would be stoically sitting there and analyzing a lot of seismological data. So, I still remember that when she's around, we used to be less noisy. Yeah. So, last but not the least, she was also in the planning team, which recommended and procured a very large funding for quantum technological initiatives in India, which got approved by the cabinet, I think, just last year. Yeah, Hema was headed the optics lab and the lamp group for several years, and then she also was the head of research facilities at RRI, a position which she held for half a decade, and uh, which oversaw many of the workshop and electrical related works at RRI. So this was a photo taken there. So as a person, I think all of us who interact with her know that she had a very fine sense of aesthetics. Some of the paintings she had in her office is something which would tell of her taste in fine paintings at least. So and she carried herself with, of course, grace and dignity, and she's a strong feminist. And even though she wouldn't be very vocal about it, in every action she did, right from taking a decision or even moving a heavy chair, she wouldn't call anyone. She would try and lift the chair by herself. So she was a very strong feminist, and she lived it in. She actually very independent in most of her everyday tasks. Never rely. I mean, if possible, never relied on other people to do everyday chores. I think that really is something which I sometimes later feel that if I hadn't known Hema, I wouldn't have known that it's possible to do so many things by one person. Like she managed to build labs from scratch. She did just not once but twice. Yeah. So even in later years when she was besieged by illness, she would actually crack jokes and say that wry sense of humor and say it's a tragic situation, but she would see the dark humor behind it, one should say. Yeah. And of course, her students loved her, especially the earlier students, because she would actually spend a lot of time in the lab. All of us who managed to get the mark or did later experiments would just say she'll be there for problem solving and for anything, even just for moral support, just sitting there. She was always available and very empathetic towards her approach to students. And so her earlier students really loved her. Yeah. Yeah, so I've been very fortunate to have known such a person, and there has been a lot of take home personal lessons for me, and also the way one has to believe in oneself and forge ahead despite what other people might say about you being, of the weaker gender. I'm sure nowadays nobody says that, but when we were growing up, this was a common reminder. Yeah. And thank you for the organizers for giving me the opportunity and for the audience to for listening to me. Thank you.